445 million years ago, something killed roughly half the genera in the sea. It was the first of the 5 great mass extinctions, and by the strictest measure, it is the second worst in Earth's history. It has no asteroid, it has no supervolcano. What it has is ice, arriving in a greenhouse world that had no idea what ice was for. To feel what was lost, you have to see the world it happened to. And that world is genuinely alien, because almost none of it was on land. The Ordovician period ran about 44 million years, from roughly 487 million years ago to 443 million. At the time of the extinction, most complex multicellular life lived in the sea. The only evidence of life on land is rare spores from small early plants. No forests, no soil, no animals ashore. The continents were in the wrong places too. The southern land masses were assembled into Gondwana, which stretched from north of the equator all the way to the South Pole. Laurentia, Siberia, and Baltica, the pieces that become North America, Russia, and Northern Europe, were separate small continents, more than 5,000 kilometers of open ocean away from Gondwana. And the seas were shallow. Vast, warm, shallow seas lay across the continents themselves, epicontinental seas, flooding the interiors, and that is where most of the life was. It was a greenhouse world, and it had been for a very long time. The organisms living in it were adapted to that, precisely, and most of them lived in the tropics. Something remarkable had just happened here. The Great Ordovician Biodiversification Event, one of the largest surges of increasing diversity in the whole history of life. Life had spent the Ordovician getting more varied, more specialized, and more local. Communities adapted tightly to their own patch of shallow, warm sea. Specialization is a wonderful strategy, right up until the conditions you specialized for stop existing. The animals of that sea were not the ones you would expect. Trilobites. Brachiopods, shelled animals that look like clams and are not. Bryozoans, building lace-like colonies. Crinoids, standing on stalks like flowers made of animal. And graptolites, colonial animals that drifted in the open water in tiny branching colonies and which fossilize as what look like pencil marks on black rock. Those pencil marks matter more than they look. Graptolites evolved fast, drifted worldwide, and died in enormous numbers, which makes them a clock. Geologists date this entire event by which graptolite species is in the rock. And in the Ordovician there were at last fish, the first true vertebrates, still small, still jawless, and quietly on their way to becoming everything with a backbone. Nabolos. Across this interval, extinction was global, and it eliminated between 49 and 60% of marine genera and close to 85% of marine species. Under most tabulations, only the end, Permian extinction, the Great Dying, exceeds it. This is the second worst thing that has ever happened to life on this planet. Around 100 marine families disappeared. A third of all brachiopod and bryozoan families went with them, along with whole groups of conodonts, trilobites, echinoderms, corals, bivalves, and graptolites. Trilobites were hit hard by both phases, about 70% of genera and half of all families gone between the Cation and the Silurian. One entire order, the Agnostida, was wiped out completely. Another, the formerly diverse Asaphida, came through with a single surviving genus. About 70% of crinoid genera died. Groups like the cystoids and edrioasteroids became very rare afterwards and never really came back. The losses were selective in a way that tells you what happened. The first pulse disproportionately hit deepwater species and tropical endemics living in those warm, shallow inland seas. There is one group whose fate is almost a signature. The Pholiomena fauna, thin-shelled animals adapted for deep, low-oxygen water, had been widespread and durable for ages. In the first pulse, it went completely extinct. A group that had shrugged off everything for millions of years vanished at once. That is what the abrupt loss of a specific habitat looks like in the fossil record. And yet, and this is the strangest thing about this extinction, it did not rebuild the world. It killed enormous numbers of things without producing major changes to ecosystem structure and without prompting any particular morphological innovation. Compare that with the end Permian, or with the asteroid that ended the dinosaurs. Those reorganized life. This one emptied it and left the furniture where it was. Diversity recovered to pre-extinction levels within about the first 5 million years of the Silurian. Fast, by the standards of mass extinctions, far faster than the recovery after the Great Dying. But something did change permanently. The Cambrian-type fauna, the old guard, the survivors of the world we met in the last volume, nearly died out here and never rediversified. And the highly local, highly endemic communities of the late Ordovician were replaced by faunas that were among the most widely spread in the whole Phanerozoic, a pattern that lasted through most of the Silurian. So what did it? The extinction comes in two distinct pulses, and they have opposite causes. The first is ice. At the boundary between the Cadian and Hernantian stages, glaciation expanded abruptly across Gondwana and shifted the entire planet from a greenhouse to an icehouse. The Hernantian glaciation is considered one of the most severe ice ages of the Paleozoic, arriving in a climate system that had been comfortably warm for a very long time. This is why this extinction is an outlier. Most mass extinctions are warming events. This one is a freeze. Two consequences did most of the killing, and neither is complicated. First, cooling. The organisms of that world were adapted to an intense greenhouse, and most shallow sea habitats were in the tropics. The polar front shifted toward the equator, and the latitude band available to warm adapted life contracted hard. Second, sea level. Locking water into an ice cap dropped sea level, and the vast epicontinental seas, the ones flooding the interiors of continents, where most of the life lived, drained. Think about what that means physically. It is not that the water got colder. It is that the habitat itself was removed. The shelf seas simply stopped existing. And because the continents were scattered rather than clustered, that retreat was especially lethal, much more so than during the Pleistocene glaciations when the same amount of ice did far less damage. In North African rock, which sat near the South Pole at the time, 5 separate pulses of glaciation are recorded. Each advance drained the seas. Each retreat let them back, carrying a diminished founder population. In the surviving warm water refuge on the Yangtze platform in what is now South China, a relict fauna hung on because the geography blocked the cold water from reaching it. Meanwhile, a new cold water community moved in and thrived, the Hernantia fauna, a high-latitude assemblage that spread along the outer shelves as everything else retreated. Life partially rediversified during the cold. That detail matters for what comes next. By the middle of the Hernantian, the oceans had a functioning Ice Age ecosystem. What caused the glaciation itself is genuinely unsettled, and the list of candidates is long enough to be worth hearing. Carbon dioxide fell from around 7,000 parts per million to about 4,400. In a greenhouse world, that is the thermostat moving. Why it fell has several plausible answers, and they may all be partly right. The appearance and spread of early land plants and of microscopic plankton consumed carbon dioxide. Heavy silicate weathering of the rising Appalachian and Caledonide mountains locked more of it away, and as the world cooled and seas fell, newly exposed carbonate platforms weathered too, feeding the cooling that had exposed them. Alternatives are on the table. Volcanic sulfur aerosols causing a runaway ice albedo feedback. Volcanic phosphorus fertilizing algae which then buried carbon. An unproven large igneous province. Even an asteroid strike and impact winter. And one genuinely strange proposal that the partial breakup of a large meteor formed a temporary ring around the Earth whose shadow cooled the planet. That is not fringe science, but it is not established either. It links to a real phenomenon. During the Ordovician, about 100 times as many meteorites struck the Earth each year as do today, after the breakup of an asteroid. The second pulse is the one that should unsettle you, because it happens when things get better. In the later half of the Hernantian, the glaciation abruptly receded and warm conditions returned. Sea level rose. The shelf seas refilled. And the second extinction pulse arrived with it, associated with intense worldwide anoxia, oxygen depletion, and eudzynia, water-carrying toxic sulfide. The cold water Hernantia fauna, the community that had just successfully colonized an Ice Age ocean, met its end here, replaced by warm, adapted Silurian assemblages. Anoxia is what happens when the ocean stops mixing. Cold water is dense and sinks, carrying oxygen down with it. That is what drove circulation during the glaciation. Warm the surface again, and that engine weakens. The deep water stops being refreshed. Oxygen falls, and in the worst case, sulfide-producing bacteria take over the chemistry. The anoxia persisted into the Rudanian, the first stage of the Silurian, which is to say, it outlasted the extinction that it caused. Some researchers argue for a third distinct pulse in the early Rudanian on the evidence of a carbon isotope excursion and a fresh push of anoxia into shelf environments already running low on oxygen. Others hold that this was simply part of the second pulse, longer and more drawn out than most accounts allow. The disagreement is about the shape of the event, not whether it happened. So, the sequence is a greenhouse world tightly specialized, then abrupt ice which drains its seas, then abrupt warmth which suffocates them. Twice, the killer was not the temperature itself. It was the speed of the change, and the fact that the ocean's plumbing responded to it. There is a modern reading of that, and it deserves to be stated carefully. This is not an analog for the present and its causes. Nobody is arguing that the Ordovician had our problem. What it demonstrates is a mechanism. That ocean oxygen depends on circulation, that circulation depends on temperature contrast, and that when the contrast changes quickly, the deep ocean can go anoxic on a timescale that matters to life in it. Everything I have just described is known from rock, and mostly from very unglamorous rock. It is worth seeing how. The two pulses are defined by graptolites. The first sits at the base of one graptolite biozone, the second coincides with another. These drifting colonies are the timekeepers of the whole event. Isotopes carry the rest. Carbon and oxygen locked into ancient shells record the temperature of the water and the state of the carbon cycle when the animal was alive. Both pulses show marked shifts in those isotopes. The rock does not merely record that things died, it records the chemistry of the water they died in. And the sea level is written in the strata themselves, shallow water rock stacked directly on deep water rock again and again as the seas emptied and refilled. There's a nice human footnote to this. The Ordovician exists as a period because two Victorian geologists could not agree. Adam Sedgwick and Roderick Murchison were both claiming the same rock beds in North Wales, Sedgwick for his Cambrian, Murchison for his Silurian. The dispute ran for years and cost them their friendship. In 1879, Charles Lapworth pointed out that the fossils in the disputed strata were not Cambrian and were not Silurian. They were their own thing and deserved their own system. He named it after the Ordovices, an ancient Welsh tribe from the region the rocks came from. It took until 1960, 40 years after Lapworth's death, for the Ordovician to be adopted internationally, which means the first of the big 5 mass extinctions was discovered inside a naming argument about Welsh hillsides. So, how should this event be ranked? It is a genuinely awkward case, and the awkwardness is the interesting part. By body count, it is second only to the Great Dying. By consequence, it is the mildest of the Big 5. It removed a vast amount of life and left the structure of the living world essentially intact. Part of the reason is what was living then. Complex life was almost entirely marine, and marine ecosystems are built on rolls rather than particular species, filter feeders, grazers, predators on the seafloor. Kill most of the species and the rolls remain. Something else fills them. That is a very different outcome from an extinction that removes an entire way of making a living. We can see that happening. In South China, sponges thrived immediately after the crisis, colonizing depleted, oxygen-poor environments while everything else struggled. And they may have helped everything else come back by stabilizing the sediment surface, so bryozoans, brachiopods, and corals could get a grip on the seafloor again. That is a lovely detail, and it is worth pausing on. Recovery from the second largest mass extinction in Earth's history may have begun with the simplest animals in the sea, making the floor solid enough to build on. The survivors also tell a story. Brachiopods that were abundant were more likely to survive than those that were rare, the plainest possible rule, and one that says something uncomfortable about specialization. The animals that inherited the Silurian were common, tolerant, and widespread. The exquisite endemics, the ones adapted precisely to one warm, shallow sea, are the ones in the extinction column. Recovery took about 5 million years to reach the old diversity. Human beings have existed as a species for a fraction of that, and the fish came through it. The Ordovician is where the world's first true vertebrates were quietly getting established, and where jaws may have appeared for the first time, late in the period. 445 million years ago, the planet cooled, drained its own shallow seas, then warmed and suffocated them, and half the genera in the ocean went away. There was nothing on land to notice, no forest to burn, no animals ashore to starve, no one to record it. The first great dying happened in an ocean, on a planet whose continents were bare rock. We know about it because of pencil marks on black shale, isotopes in the shells of animals that died in the wrong water, and 2 Victorians who could not agree about whales.